Again, welcome to Statistics DSRT 734 class. And our main topic here is chi-square test, independency. Again, in our previous lecture, we start with the chi-square test. And we saw the process of the hypothesis testing using the chi-square test. In these lectures, we're going to use the chi-square test to find whether two variables are independent. So that's why, again, our main topic is independency. So the main objective is use the contingency table to find expected frequency. Also use a chi-square distribution to test whether two variables are independent. In our previous lectures, we discussed about what is again expected frequency and what is also observed frequency. In order to find the test statistics for chi-square distribution tests, we need to find the expected frequency and also the observed frequency. So again, this lecture, this is a new topic, how we can use the contingency table to find the expected frequency. In our previous lectures, we also find the expected frequency because again, when you are doing chi-square test, the formula is the difference observed and expected frequency square over the expected frequency. So we need to find the expected frequency. So we start with the contingency table. And we say R by C. This is R here stands for row and C stands for column. So we know a table consists of rows and a column. The intersection of the row and the column is the small box that we call the cell. So again, contingency table shows the observed frequency for two variables. And also the observed frequencies are arranged in R rows and also C columns. So again, the contingency table will always shows the observed frequency. As previous lectures, we went through chi-square distribution test. Remember, the observed frequency is the values that were given to us. Observed frequency always given to us. Then we have to find the expected frequency. The same concept here. But here we are going to use the contingency table to find the expected frequency. So here we say that the contingency table always will show the observed frequencies for the two variables. And also the observed frequencies are arranged in rows and columns. So the intersection of the row and the column, again, is called a cell. So this is a nice example here. Again, this example is for contingency tables. So here we say a contingency table shows the result of a random sample of 550 company CEOs classified by age and the size of company. So we have again a contingency table here. And we can see that we have again a total of 550 company CEOs. And they are classified by their ages. So the rows are ages. So the first, we have the size of the company, small/mid-size, and then large. So to my left, we have the small, mid-size, and the large. So we have two rows. The columns are the ages. So from 39 under, 40 to 49, 50 to 59, 60 to 69, and 70 and over. So for example, I will pick 69 here. And the number of CEOs 69 here means we have these CEOs, their ages between 40 to 49. And also these CEOs are in a small and mid-sized company. So this is an example of a contingency table. Consists of the rows and columns. Here our columns are the ages, and then the rows are the size of a company. So now, if this data is given to us, we can find the expected frequency, and that's the next step. So here we again said, the contingency table shows the result of a random sample of 550 company CEOs classified by age and the size of a company. So we have the age as the columns and the company size as the rows. Now we said, assuming the two variables are independent, which is the size of the company and also the age of the CEO. So if these two variables are independent, you can use the contingency table to find the expected frequency for each cell. So here we are zooming again the two variable, which is the company. And let me go back one more time. So the company size and age, they are two variables, and these two variables are independent. If they are independent, then we can find again the expected frequency for each cell, which means when we look at this cell here, we have 1, 2, 3, 4, 5. So we have 10 cells, 10 values. Each value is in one cell, so 10 cells. So that's the step we're going to follow now. So to find the expected frequency for cell, we say cell RC. So if it's the first row, first column, then we say E11. So the first row 1, first column 1. Second row 2, first column 3. So it will be E23. So here to find the expected frequency for cell ERC in a contingency table, this is our formula. We multiply the sum of the row, which means we had all the value on the row, times the sum of the columns. Then we divide by the sample size. So the sample size is how many companies that again. So again, that is the formula, the sum of the row R times the sum of the column C, and divided by the sample size. So we're going to use this as our example. So the same data set, we have the company size and the age. We intentionally put the total here because we need it. So the total for under the age of from 39 and under is 47. That's for both company. Small size, mid size, and large is 47. Between the age 40 to 49 is 87, 50 to 59, 193, 60 to 69, 180, 70 and over is 43. Now, all the CEOs for small and mid-sized company, their total, regardless of the age, their total is 300. All the large company size, their total again is 250. So when we add all, we get 550. So this means we have 550 CEOs. Now our sample size will be 550. So let's start with our expected frequency. So here we have the marginal totals. We can see small size and small and mid size together. Large 250, 300, the total is 550. We have under the age or the total. When we had all this also, we should get the same 550. So the whole concept of finding again, we have 10 values, which means we have 10 cells. So the expected frequency will be 10 values or the 10 cells. So here we can see that we are trying to find the first row and the first column, E11. Again, the first value should be the row, the second value should be the column. So E11 will give me 300. Remember, we say what? The sum of the row. The sum of the row is 300 times the sum of the column is 47 divided by the sample size, the total 550. So again, to get E11, the expected frequency for the first cell, row 1, column 1. Actually, we have it here again. The formula is ERC, the row and the column, sum of row times sum of column divided by the sample size. So sum of the row is 300, sum of the column is 47 divided by 550. Then we go to we are in the first row, second column, E12. So this is my E12. The same thing, sum of the row, so that is 300. This time the column changes. Previously we were in the first column, 47. Now the second column is 87. So, and we're still in the first row. So the row values, the row sum would not change. So we have 300 times 87 divided by the sample size, which is 550. So that gives us 47.45. Then we move to the next column. We are still in the first row. So the sum of row is still 300 times the sum of the third column is 193. So it will be 300 times 193 divided by 550. And that will give me 105.27. Then we move to the fourth row. Fourth column. We're still in the first row. So the sum of the row is still 300. But this time, the fourth column, the sum is 180. So it will be 300 times 180 over 550. That give me 98.18. Then we move to the last column. We have 5 columns, so this is our 5th column. So the sum of the row, again, we're still in the first row, so we still have 300. The sum of the 5th column is 43 divided by 550, and that give me 23.45. Now we move to the second, we finish with the first row, so now we're going to the second row. So we start with the second row and also the first column. So second row, the sum is 250. First column is still 47. So we have 250 times 47 divided by the sample size. And that gave us 21.36. We move to the second column. So the second row again is 250. Second column is 87 divided by the sample size 550. That gave us 39.55. Then we move to, we're still on the second row, third column. So E23 will give me the second row is 250. And this time the third column, again, is 193. So 250 times 193 divided by 550, that gave us 87.73. Then we move to the fourth column. So we are still on the second row, fourth column. Second row, the sum is 250. And this time the fourth column, the sum is 180. So 250 times 180 divided by 550, that give me 81.82. And the last cell, which will be the second row, 5th column. So again, second row, the sum is 250. 5th column, the sum is 43. So 250 times 43 divided by 550, and that gave us 19.55. So here, our example here is using the contingency table to find the expected value. The expected value depends on the number of values we have or the number of cells we have. Here we have 10 cells, so we have 10 expected values. So now let's move on to our chi-square independency test, and this is our main objective for these lectures. Again, in order to do the chi-square independency test, we're still going to use the contingency table to find the expected value. So it's like we continue. So how do we do chi-square independency test? Here they say use to test the independency of two variables. So in our case example here, we want to test if the CEO ages and the size of their companies, these two variables are independent or dependent. Dependent means, again, your age will determine whether you are working in a small size or mid size or large size. Independent means it doesn't matter your any age, you can work in any size of a company. So our goal of this chi-square distribution test is to test if two variables are independent. So this is a very nice example we are going to use. We want to determine if a CEO age determines the size of his company. If it determines the size of his company, then the two variables are dependent. If it doesn't determine, then they are independent. So here we say can determine whether the occurrence of one variable will affect the probability of the occurrence of the other variable. And that's the whole concept of dependent or independent variables. So if it's a dependent variables, it means the first variable have effect on the second variable. Or our example again, if the age of CEO and their size company, if these two variables are dependent, it means the age of a CEO will determine the size of company that is the CEO. If they are independent, that means the age, a 40 years old CEO can work for a large company, also he can work for a mid-sized company, and he can work for a small company. So now we want to do our chi-square independence test. So first, to find the chi-square independence test to be used, we have to have the following condition. So here we say the observed frequencies must be obtained by using the random sample. So which means our data must be collected using random sample, the observed frequency. Always the observed frequencies will be given, same as our previous lectures when we are doing the chi-square distribution test, not independency test. Observed frequency is always given. Then each expected frequency value must be greater than or equal to 5. So all the values you get for expected frequency, if any of the values is less than 5, then we can use a chi-square to test if the two variables are independent. So that's the two conditions. Now, if these two conditions are satisfied, then the sample distribution for the chi-square independence test is approximated by a chi-square distribution with R minus 1 times C minus 1 degree of freedom. So here in this testing, to find the degree of freedom is not again the sample size minus 1 or the sample size minus 2, as we saw in the regression t-test, hypothesis t-test. No. Here now is a new formula to find the degree of freedom if we are doing the chi-square independence test. Remember, independence test means we have two variables. We are testing if they are independent. So by looking at the contingency table, we will see the values of those two variables together. So in order to get the degree of freedom, what is the row, the size, the number of rows we have? That's, for example, in a company size, we have 2 rows. We combine the mid-size and small as one, and we have the large. Now for the column, we have 5, because we have 5 category of age brackets. So if we are doing the same example, then we'll say 2 minus 1 times 5 minus 1, and that will give us the degree of freedom. Because again, chi-square and t-distribution, we always need a degree of freedom, because that tells us in the table the row that we go to is the degree of freedom. And also the formula is the same as our previous lecture. So if I want to find the test statistics for the chi-square, it's again the sum of the difference of the observed and the expected frequency, all squared divided by the expected frequency. And this is the formula we use in our previous lectures also. So the O means the observed frequency, which is always given, and E means the expected frequency, which we always have to find it. And in this case, again, independence test, the test is always a right tail test. There's no option of left tail or two tail. It's always right tail test. So let's put it in words, how the steps of, again, doing the chi-square independence test. Again, as we said earlier, independence test means we are testing if 2 variables are independent. So this is hypothesis testing. So the first thing we do, we have to identify the claim. We need to state the null hypothesis, and also we need to state the alternative hypothesis. So here we state the HO and also the HA. Then the second step, we specify the level of significance. remember, it's almost the same step as our previous hypothesis testing. The level of significance is very important. With the degree of freedom, we can find our critical value that will separate the rejection region from the accepted region. So when we specify the level of significance, the next is to find the degree of freedom. So the degree of freedom, and again, the level of significance, we can be able to find the critical value for the region between rejection and so we can see the steps are the same as previous lectures. The difference is the formulas changes. So if I know the level of significance, the alpha, and I know the degree of freedom, then I can be able to determine the critical value. So the critical value, I'm going to use the chi-square table, and I'll go to the degree of freedom will be in the table to be our row, and the level of significance will be our column. So in the intersection of the value of degree of freedom and also the level of significance alpha, we can get the answer for the T. I mean for the chi-square from the chi-square table. And that value will be our critical value, which will separate the rejection region from the accepted region of HO. Again, we're going to do an example soon. So after we find level of significance, degree of freedom, we get a critical value, then we can determine the rejection region. Then after that, we find the test statistics. So the test statistics value, if the value falls in the rejection region, then we are going to make our conclusion that we reject the HO. If it falls inside the accepted region, then we are going to make our conclusion that we fail to reject HO. Again, this is the formula, the same thing, chi-square. In this case, observed frequency is given. We just need to find the expected frequency. Then we finish. We make our decision to reject or fail to reject the null hypothesis. Then we are going to interpret the decision in the context of the original claim. So we can see that the steps here again, they are the same as our previous chi-square distribution test. The only difference is that this time we are testing if two variables are independent. Previous was different. So we are going to use the same example, but this time you can see that they gave us the observed, because as we said earlier, observed frequency have to be given. So here they say using the age and the company size contingency table, we want to test if age and company size are independent using chi-square. Can you conclude that the CEO ages are related to the company size? So that's our, if they are related, then they are dependent. If they are not related, then they are independent. They gave us the alpha value to be 0.01, which is very important. And also the expected frequency, we don't want to find it again. You quite remember we found it in our previous example. So to find the expected frequency, we said, for example, I'm in the first row, first column, the sum of the row times what? The sum of the column divided by what? The size. So again, we find, let me go back one more time, very quick here. Again, we covered this, so that's one example here. So let's say we are looking for Y21, which is second row, first column, the expected frequency. So second row is here. The sum of the second row is 250 times the first column is 47. So 250 times 47 divided by what? The sample size 550. That gave me 21.36. So again, we're going to continue with the example. So that's how, again, we find the expected frequency. So that's the values we put down here. So we have all the expected frequency value. Those are the value in the parentheses. They are the expected frequency. So in our original example, the observed frequency is given, you have to find the expected frequency. And we saw the process again. So now we are going to follow the steps. Our goal is that we want to check if company ages are independent of company size. So our null hypothesis, we say the ages are independent of company size. So the HA alternative hypothesis, I have to go against it. So we say ages are dependent on company size. So we are testing if these two variable age and company size are independent or dependent. So we have the alpha value already given to us. The degree of freedom, we saw the contingency table. We have 2 rows, so 2 minus 1. We have 5 columns, so 5 minus 1. 2 minus 1 times 5 minus 1 will give me 4. Okay, so since I know the alpha, the level of significance, and I know the degree of freedom, I can find the critical value by going to the chi-square distribution table. So when we went to the table, we get 13.277. Again, we went through our first lectures when we used the chi-square in the previous. We show how to use the chi-square table. And when you go to a chi-square table, the degree of freedom is your row. So look for row 4. Then the alpha will be on your column. Look for 0.01, or again, this case it will be 1%. So the intersection of alpha of 0.01 and degree of freedom, which is the row of 4, the intersection of that value is 13.277. Sometimes it's very straightforward. Sometimes the alpha will be in percentage, but again, 0.01, if your table said it's in percentage, then it's 1%. If the table is in decimal, 1% means 0.01. So alpha is always at the column, look for the value. Then degree of freedom is your row. I'll go to row 4. The intersection of the column and the row give me 13.277. Okay, so if we know this, then we need to find our test statistics. Actually, that's why we find the expected frequency. So we are going to get 10 values. Remember, we have 10 cells. We already observe frequencies given. We already find the expected frequency. So we just plug in all the values. The first row, first column, remember, we have 42 for the observe. We find the 25.64 as our expected frequency in the previous example. So 42 minus the, and also the expected frequency is the values in the parentheses. So we have 42 minus 25.64 all squared divided by 25.64, because the formula is 0 observe minus expected frequency all squared divided by expected frequency. So we do that again, it's a sum. So we do that for all the 10 values, then we add all together. So again, one more time, always the observed frequency will be given. Expected frequency was our first example we did, where we use the contingency table to find the expected frequency. We go the first row, first column, and we say the sum of the first row times the sum of the first column divided by the total sample. And that will be our expected value for first column, first row. Now, example again, what is the expected value for the second row, first column? Okay, the sum of the first row times the sum of the second column, that's the first row, second column, divided by the sample size. So we find out the expected value. So if we know this value, we finish. We are going back to our rejection region. See, we have 13.277. So 77.9 fall inside our blue area. So that will be to reject the HO. Always the brown area is to accept region, accept HO region. So here we are going to reject HO. So we interpret our answer that there's enough evidence to conclude that the CO ages are dependent on company size. Depend on the company size. Because remember, HO said CEO's ages are independent. The CEO, their ages are independent. And based on this conclusion, it falls under rejection. So rejection of HO means they are dependent. So this will be the conclusion of our lectures. Again, in these lectures, we are learning how to use, again, chi-square distribution test to test if two variables are independent. When we say two variables are independent, we mean is X variable causes Y. So for example, we can have two variables for a lung cancer and another variable for smoke cigarette. So here we want to know if these two variables are independent. If they are independent, it means some people may smoke cigarette, they may have lung cancer. Some people may not smoke and they still have lung cancer. So this means it's independent. But if majority is when you smoke cigarette, you have lung cancer, then here we have again dependent. So again, in this our short lectures, we learn how we can test if two variables are independent or dependent. So again, wish everybody the best. Thank you.